Hey everyone, I'm Beth, and I'm going to be talking about METR's research on evaluations. So this will be 3 parts. First, I'm giving an overview of sort of what we're evaluating for and why. Then Daniel will be saying a bit about how we make sure that we're getting the full capabilities out of the models when we run the evaluations on them. And Ted will talk about the tools and infrastructure that we use to run this. So a very quick background on me. I was formerly a researcher at DeepMind, then at OpenAI. I was working on evaluation things at OpenAI. And in 2022, I was kind of thinking that there should be more external third-party evaluations work that's happening outside of labs. So I left OpenAI to start this project. So what are we evaluating? When people think about sort of AI misuse, usually what they're imagining is more like there's some existing bad actor or criminal or whatever who's doing something we don't like, and they use AI to help them do this faster or to do a more advanced version of it or something like that. But it's still kind of fundamentally like there is a human and they're using the model to do something. That's not what we focus on. We're focused specifically on threats based on models that can do really a lot of stuff themselves. So rather than just assisting a human to do a bit more of what they were doing anyway, these agents can like make more agents, set them up to do various different things, build their own tools, and then do much more than the case where they're just assisting a human. And in particular, sort of the eventual scope of harm or chaos or whatever caused isn't dependent on the resources of the initial actor. It can kind of get out of control, even if the starting resources were very small. So in order for this to actually be plausible, obviously these AI systems need to have a lot of capabilities. So they probably need to have the ability to write code or at least use computers via a command line. They might need hacking and cybersecurity capabilities. They'll definitely need to be able to improve and modify themselves and their tools. And they'll need to sort of be able to do research, communicate with humans, look up information they need, that kind of thing. So obviously models are not good at doing all of these things to the level that they would need today, but we're kind of making tasks that track these capabilities and seeing, tracking when models start being able to do these things. So, for example, for the sort of self-improvement or building more tools piece, we've made various tasks that, are intended to capture this. So intended to capture kind of being able to do machine learning research or being able to kind of make improvements to an algorithm, being able to build new tools for a language model agent to do to browse or to solve a certain kind of task. Or for coding challenges, there's like lots of stuff that you can do here. And we're, in the terms of sort of difficulty level of these tasks in general, I'm giving examples from the sort of upper end of our range, which is where we're looking at, can the model do something that would take a human expert, several days to a week to complete? So this is, again, a long way beyond what models are capable of now. The sort of, the phishing or cybercrime, we could say, like, can you do the whole phishing attack end to end? And also some examples of like easier tasks, kind of capture the flag or other hacking or reverse engineering challenges where it's more like you just have to sort of solve a particular kind of problem or break a particular sort of thing. Like the basic idea of any of these tasks is like there is some input and then an agent that could be a human or a language model gets time to kind of work on the task. So they can run code or use different tools, make notes to themselves, think to themselves, save things to files, look things up on the internet. And then eventually they need to produce some kind of artifact or output at the end that's the like solution to the task or the kind of completed work product. So yeah, in the like reverse engineering case that I just mentioned, the input would be like you get a binary file, and then you can run various tools and things on it, and then eventually you have to output what password this binary file is checking for. And like, yeah, that will be like the password that when passed as an argument to that file will give you like, well done, you completed the task. So this is a real example of one of our agents doing the tasks. This is real but cherry-picked. This is maybe a task that takes like a human with some security background half an hour-ish, something like that. So it's pretty like substantial task, and this is one of the more impressive agent runs. So yeah, obviously lots and lots of steps omitted here, but some examples of, it uses a command line tool to get some more information about the contents of the file. Then it deduces various things. It realizes, that XOR, somewhere the password's being XORed with something. So if it can find where XOR is being used, then it will know that that thing is related to the password. It realizes then that the tool it's currently using won't give it enough information to figure that out, so it uses a different tool. And eventually, in this particular example, the agent is able to succeed. So, yeah, this is pretty different from a just kind of question and answer or prompt and completion, as kind of more typical ML benchmarks are. Because it just really like involves a lot of steps of the agent thinking, trying different things, making incremental progress. You're using different tools, realizing that the tools didn't work. Then recovering from kind of errors or going down a blind alley. So for these kind of even these tasks which are on the relatively easy end of the tasks we're developing, there's a lot of general capabilities of sort of being able to do anything at all and like make progress sensibly and make good decisions about what to try next. That's kind of captured even in these easier tasks. So our key goal at the moment is to propose a procedure for evaluating for these dangerous autonomous capabilities that has various properties. Basically, we want it to be something that's like well specified. We can write it down now, and it's something that a lab could actually just run, or an auditor could just run. That it doesn't depend on sort of someone gets to make a judgment call about how scary this thing is, but that's fairly detailed. In as much as there's human decisions, it's based on fairly detailed rubrics of like, did it have this property? Did it have that property? That it's affordable enough, at least for labs that are doing large training runs, and that it's costs less than $2 million and takes less than 1 month for a small team to run. And yep, the important bit, which is like, we think if model development is kind of guided by these evaluations, that keeps risk to an acceptable level. So we're trying to make the evaluation that has the highest ceiling in terms of like how high capabilities you can get while maintaining all of these desired properties. This is something we have a draft of now and hoping to release pretty soon, but it'll be a very this is the initial version, and will be improved over time, but we do it there is actually a concrete procedure that you can follow here. So that includes things like the exact list of tasks and the code to set up and run all those tasks, guidelines for actually sort of setting up the model to run on the evaluation, to run on the tasks, and checks you need to do to make sure that everything worked properly, tooling for actually, setting up your agents and running them on the tasks, and then our, kind of proposed thresholds that indicate different levels of risk. So we're like, if you see this much success on these tasks, this is the mitigations we think might be needed. Yeah. So, this is our list of tasks. It goes from things that take humans a few minutes to things that take humans a few days. We do want to keep adding harder tasks beyond this, but hopefully this is hopefully, fingers crossed, models are not going to blow through all of these too soon. So Daniel will talk more about this, but basically we have kind of procedure that you need to follow to make sure that you're not accidentally underestimating the capabilities of the models. Like, for example, one thing that's pretty important is to make sure that when you're running the tasks, the compute budget you use for the agent to do the task is proportional to, or, and leaves a bit of margin compared to the cost it would take to pay a human to do the task. Because, if we're intuitively asking with a task like, can the model, is the model sort of competitive with a human programmer spending a few days sort of thing? If you're instead accidentally asking the question, can the model do this task that would take a human programmer a few days for 1,000th of the cost? Like, that is a different threshold that has different implications for the level of danger. So we're saying, you need to make sure that you're not just underestimating model capabilities because you're expecting them to do things like extremely quickly or extremely cheaply. And some other procedures for how you should have separate development set and evaluation set of tasks, and making sure that you're not getting spurious failures on those tasks. Ted will talk more about our platform, but the kind of evaluation guide that we're making will include some very simple agents you can use as a baseline, and enough infrastructure that you can actually, relatively easily set up things to actually run the models on the tasks. So thresholds kind of roughly corresponding to these task buckets. So we have some sense of for a model that is able to do these kinds of tasks, what do we think the appropriate mitigation is? And there's some mapping there. And then there's also the distinction between when you measure capabilities, you'll see the model's able to do these tasks, not this one. But we want to make some adjustment for ways that could be wrong. So both, if there's more elicitation techniques that would be developed over time, or ways to get better performance out of the models, or if the kind of question that this evaluation is being used to determine is is it safe to scale up a model by, say, 4x effective compute, or just how will the world change over time in terms of the cost of compute and running these different models, or how easy is it for the models to interact with the world in various ways. Depending on kind of all those parameters, there's some amount of safety buffer that you need to leave, and that will then give you some kind of what is the highest level of capabilities that's plausible given the measured score. And then basically you need to have the mitigations that are in line with those presumed capabilities. So that was the kind of outline of overall procedure, and we're currently kind of getting feedback on this and hoping to have something out pretty soon. So that's all from me, and I will hand you over to Daniel to talk about getting the models to try their best.
All right. Cool. Let's keep going. Yeah, I guess I can give a quick intro about myself. I'm Daniel Ziegler. I work on improving agent capabilities at METR, in particular, to make sure that we're not accidentally underestimating performance. Beth already talked a little bit about this, and I'll talk a little bit more about that now. And before that, spent some time at Redwood Research, and also spent 3 years at OpenAI working on some of the initial implementations of reinforcement learning from human feedback, and also some of the training infrastructure behind GPT-3. As Beth already said, we think it's really important to unlock the full capabilities, or at least as many of the capabilities as you can in a reasonable amount of effort, when you are doing evaluations, so that you're not accidentally missing things and underestimating the performance. We know from the literature that large language models can be quite sensitive to prompting, depending on exactly how you try to elicit your answers. You may get very different numbers. And what we found is that that's even more true for large language model agents. There's just many degrees of freedom in how you build them. And there's a lot of ways that you can sort of accidentally reduce performance in ways that are relatively easy to fix. So just to give some examples, sometimes models might refuse to do a task because it's unethical, or because they claim they cannot do it, even if it might be worth a shot anyway if they're acting as an autonomous agent, or they might just be incorrect about that. Sometimes they might just give up and ask the user for help. Again, being sort of more of an assistant than an actual autonomous agent. They can get stuck in loops. There's a bunch of different kinds of failures, and these are sort of fixable to varying degrees, but many of them don't reflect underlying limitations of the capabilities of the model. So I want to give one particular example that we encountered in our work, where an agent claimed incorrectly that it was unable to do something and gave up as a result. So here, this is a sort of reasoning step in the middle of a trace, an execution trace for an agent that was trying to perform a simple SQL injection task. So it had this service at a particular domain that was instructed to try to exploit, and it does some, relatively reasonable reasoning about what plan maybe it should follow, but then it says, but this VM doesn't have any general internet access, so it won't be possible to directly interact with the given service, which is incorrect. And then it just kind of gives up and says, unfortunately, given the current VM limitations, these steps remain theoretical and untestable. And, it does continue for a few more steps, but it doesn't succeed because it sort of thinks it's not possible. But what we found is that this model actually is smart enough to realize that this is not a good reasoning step. And the way we found that is we trained a copy of the model to be a so-called reward model or rating model. So we collected a bunch of human annotations on actions or reasoning steps, where they said, yes, this was, this seemed good or this seemed bad, and assigned different ratings. And our reward model thinks that this, is able to recognize that this is a bad reasoning step, and is able to reject it. And so if we sample some more possible reasoning steps from the same context, we get a different one that has some kind of similar sort of high-level plan, and then it just sort of decides to jump right in. It says, first, let's register a new user. And in fact, when you continue the run from this point, it does succeed. And it succeeds in figuring out how to exploit the SQL injection. And our reward model was able to recognize that this was a better reasoning step. So with a modest amount of effort, we were able to get this model to be able to take better actions and be more successful some of the time. Of course, there's a lot more you can do. There's many kinds of sort of post-training capability enhancements that are relevant for agents. There's a lot of iteration you can do with prompting, tuning things like how verbose should the reasoning be, and just many kinds of things that turn out to have a pretty big influence in performance. There's various kinds of better tools you can add. So we noticed that our agents were struggling to edit files well using just shell commands. So we gave them some more specialized file editing tools. We also, iterated some on browsing tools and web interaction. And there's a bunch more stuff you can do. There's obviously many kinds of fine tuning, from supervised learning on human demonstrations to RL from human feedback, et cetera, and also ways of giving the agent more and more thinking time, including chain of thought and the best of n procedure that I described. That's sort of using the kind of reward model that I described earlier. You can sort of say, okay, cool, let's make our agent think of multiple possible next steps, and then ask the reward model which one it thinks is best, and then proceed with that one. And this is a way to sort of use more thinking time to get a more powerful agent. And there's lots more you can do in this space. And as we iterate on our agent performance with all these kinds of techniques, one thing that we think is really important is that you sort of don't do that on your actual evaluation tasks, which you're going to use to measure performance at the end or to measure the level of danger at the end, because that would risk overestimating the level of danger because you might overfit on those tasks. So instead, we have some other tasks. We keep the ultimate test set held out and have sort of a development set of tasks that represents similar capabilities, but it's not literally the same set of tasks, which is standard ML practice, but important to remember. And yeah, so what we wanted to know was sort of, well, how much of a difference does this all make? Like how different are your results when you really try to push the agent capabilities using a modest amount of effort versus not? So we sort of did a case study with a somewhat random grab bag of tasks that are like roughly within range for our current agents. And we worked with GPT-4 and GPT 3.5. And so this graph sort of represents improvements in agent performance over time, mostly on GPT-4 as a result of different kinds of post-training enhancements done by OpenAI and by us. So we start out with this like point over here for the GPT-4 base model, with some few shot prompting and some very basic, sort of basic agent scaffolding, and it does very poorly on these tasks. And then later, if we jump to the released version of the model with very similar scaffolding, it already does much, much better. And the version of the model that OpenAI released 3 months later, with more, we don't know exactly what they did, but there was certainly more training, more human feedback, and probably some more agent training for ChatGPT. That is also another noticeable leap on our measurement here. And then we sort of did some work on top, and added a bunch of different tools and our reward model that I described earlier, and got a little bit better. And so. Yeah, so what do we take away from this? I wouldn't take these exact numbers too seriously. It's sort of a, depending on which tasks you use and depending on which exact techniques you apply, et cetera, like the numbers can look different. But I think that like the takeaways here is, starting from the same base model, the post-training that OpenAI did and that we did sort of made a very large difference in performance, sort of comparable to the difference between model generations, right? Like this is the GPT 3.5 point over here, including our, the reward model and everything. And another lesson is like, it's sort of hard for us outside of a big frontier AI company to make a large improvement. So, the gain that we made was only modest. But the hope is that this kind of research can hopefully help ground like how much of a safety margin do you need to leave, sort of depending on how hard you try to actually get the capabilities out of your agent. And if you're just starting with a base model and you're doing some few shot prompting, like you're going to need to leave a lot of safety margin. Whereas if you push it harder, maybe it's less. But we don't know sort of where the limit is here, and we would love to understand that better. Even with still a reasonable amount of effort. And it's also very possible to accidentally nerf the capabilities of your agent. So like AutoGPT, we with the same model, performs substantially worse. There are some better open source agents out there, but yeah, it's easy to underestimate your capabilities. Yeah, I think that's the main stuff I want to say for that. So some takeaways. Yeah, we think, it's important to, when you want to run some evaluations first, maximize the performance of your agents or whatever on a dev set. Make sure to give your agents enough of a token budget, so that they're actually able to spend, at least as much money as it sort of would have taken to pay a human to do the task. That does actually make a pretty big difference. Give them enough thinking time. You should, as Beth mentioned, review the transcripts of your agent executions for any spurious failures that remained, including things like just giving up on the task, like I mentioned. And then, depending on how things look, you should apply some amount of safety margin to account for further possible improvements. Yeah, cool. Any questions based on that before we move over to Ted?
All right. Hi, everyone. I'm Ted. I'm going to be talking about the platform that we've built that supports all this work. Let's see. A little bit about me. Former founder, sort of, Y Combinator back in the day used to make consumer products used by tens of millions of people. Now I make like ugly products used by small numbers of researchers. So one question is like, why did we build a platform at all? It turns out that doing these kinds of autonomous capability evaluations requires some amount of like fairly specialized tooling that's different from the kinds of things you might build for other sorts of evaluations. We're actually on like our 4th generation of our internal tooling, and we sort of rolled the lessons from the earlier versions into the more recent one. And it's actually been adopted by the UK AI Safety Institute, like kind of wholesale, to help power their evaluations. So key ingredients of a platform, you need a way to define like agents, like the kind of work that Daniel was just talking about doing. And ideally that can be done very flexibly. So you can sort of make arbitrary agents that work in any kind of way. You need a way to define tasks. Those should also ideally be as flexible as possible. And then like a way to actually have the agents attempt the tasks. And concretely, you can picture like, hundreds of virtual sandboxes in the cloud where the agents are attempting to do the different tasks in parallel. Like one little concrete demo is basically a command line tool where this is like starting a run on a capture the flag computer security challenge. You can just sort of say you want to like run against this particular task. And then you sort of get a UI where you can sort of see the trace of the agent as it's attempting. It's kind of trunks along and makes some progress. Let's see here. I'm just going to move on from that. I can't move on that. Yeah, it's like a lot of different kinds of things can happen in these runs. So, for example, here is an example of an agent trying to buy a dress on Amazon. This is in the category of task where if the agent cannot complete it, we're not too worried yet. Like, if the agent can't buy a dress, then probably can't do anything too dangerous with its autonomous capabilities. And in doing this, it's like trying to browse, and it like runs into like a CAPTCHA. And one of the things that it has is we gave it like a way to like describe images generally, and it decides to like use that tooling to like see what's in the CAPTCHA, and then like gets the answer right, and sort of makes it past that point. And so in this case, we didn't do, when we added like the ability for it to like call a vision model, we didn't anticipate it would suddenly be able to like solve CAPTCHAs. That's not even why we actually added it. It just turned out, it kind of can. And so this points to like it's important to have the tooling be capable of having lots of different kinds of capabilities in the agents and situations that the agent can encounter. Otherwise, you're sort of not gonna see this stuff. Also, like another random example, an agent learning to use like a voice cloning API. You could imagine this is some kind of like useful in some kind of targeted phishing scenario where you're trying to trick somebody. And in this case, it just goes and like reads the documentation online the way that like a software engineer would, and then uses the API correctly. So how does this platform get used? It turns out there's a bunch of different kinds of users. They all want different things, which is always fun. So there's people who are like making tasks, and that's actually kind of involved because you also want people doing like quality assurance runs on those tasks to make sure that there actually aren't any bugs. And you also want to do, like Beth was referring to, like measuring how hard the tasks are in terms of how much you'd have to pay a human to solve them. And so you sort of need like workflows for all of this. You've got like people trying to unlock the latent capabilities of the agents, like Daniel was talking about. You've got fine-tuning data labelers who might be coming in and helping build the reward model data set. There's people working on like responsible scaling policies who want to be able to like point to particular thresholds and things, and it's useful for those to be able to be sharply defined in terms of specific tasks and outcomes. And you've got qualitative researchers where we found it's actually kind of important to spend, we'll get to more of this later, but to actually build qualitative impressions of the model's capabilities and strengths and weaknesses. And so you want your tooling to support that. It's much better to be like, have people who are spending a lot of time reading transcripts rather than like treating it like a black box. And then if you're actually doing an evaluation, you want to actually, run all of this and sort of generate a report and things like this. Let's see. So what are the capabilities of the platform that allow for all of this? One thing is like scale. At this point, we've done around like 60 or 70,000 runs of agents against tasks in sort of the course of all the research that's been happening. you want to be able to do like some about this in bulk. If you're generating a graph like Daniel showed earlier, you kind of want to be able to do lots of runs at once. Ideally, you don't want to have any like mishaps. You want to be able to like have like tasks that don't have access to the internet or only access to specific kinds of the internet. You want to be able to connect out to labs. And then, this is getting a little bit into the weeds, but like when you're developing an agent or a task, it's actually really important that the developer experience for that is good. And if you like, we could actually stand to be a little bit better here. We've put some work into it, but like it's easy to accidentally make it so to start up a new run of an agent against a task, it takes like 3 minutes of wait time or something, and that's like pretty sad. So trying to get this loop fast is helpful. And then we also have some functionality around branching and time travel. So a lot of times, if the agent is going along, it might reach a point where there's multiple next possible options it could make. This is like what Daniel was talking about earlier with the rating model choosing between multiple options. And in a fully autonomous run, the agent will actually just like choose the best rated option and continue on. But sometimes a human looking over this might be wanting to build a qualitative understanding and wondering what would have happened if the agent had chosen a different option, or if the human even want to inject their own written option to see what would happen next. And so there's some tooling support for this kind of like time travel back and like branching into a different thing to see what would have happened next. And this is like pretty helpful for building a qualitative understanding. In particular, you can see if the agent is getting stuck at a certain point, if you help it over that point, does it immediately fall on its face again, or does it then go and like solve the rest of the task? And like, it's pretty important to be aware of like which kind of scenario that you're in. I'm gonna talk a little bit about our sort of format for tasks. We've made a lot of tasks. Each of these sort of like, there's multiple columns of like lines of these little like white text. These are each a task family, which inside of them can actually have multiple actual tasks. So I think we've made maybe around 100, order of 100 task families, an order of 1,000 tasks. These cover a bunch of different areas like Beth was referring to. There's sort of, autonomous replication. Can you like copy yourself onto another server on the internet? Self-improvement stuff, cybercrime stuff, cybersecurity stuff. And a bunch of our tasks are actually, for now at least, just around sort of general agency. Can you just sort of do stuff? This is a really important component of doing anything, is actually being able to do anything at all to begin with. We've discovered that there's sort of two kinds of tasks. It's like low effort, like mass imports of existing tasks. One downside here is the solutions can be online. And so maybe, if the agent does solve the task, you're always going to have this question in your head. Was it sort of part of the training data? Did this create an issue? And also like high effort custom tasks where it can be really much more specific to the threat model of concern. These are a lot of work to make, but hopefully sort of more informative on a per task basis. So an example of a high effort task is like, is Timothy here? He made this task. Anyway, there's a develop a computer worm task where the agent is like presented with a network of computers running an old version of web server software, and it's like the task is to like write a worm that will go and like spread across and infect the whole network. And developing a task like this takes a pretty serious amount of work. It turns out, and so. This is sort of poses a problem because by default, it's actually really hard to share tasks. Like, maybe there's different eval teams at labs, and there's like us, and there's now governments, and everybody's kind of trying to build their own sets of tasks. But by default, it's really hard to share these across organizations because there just ends up being a lot of like local idiosyncrasies in how precisely the task is defined. And it's actually easy to accidentally not actually fully define your task whatsoever and have sort of a lot of ambiguity around it. And so this is like a sad state of affairs because it results in a lot of duplicated work and also makes things less reproducible. So we've open sourced recently a task standard. The UK AI Safety Institute has adopted it, and other folks are starting to adopt it. And there's interest in sort of writing adapters that make tasks in this format work in other places. And the benefit here is we get to share. There's a public GitHub repository, as you might expect, which includes like a workbench that anybody can use for sort of developing a task in this format on their local computer. And the hope is that this will prevent a lot of duplicated work. And we're making a bunch of improvements around like support for GPU tasks involving GPUs and virtual machines and things that can't be containerized and things like this. And the ultimate goal, we're kind of working on it for now, but the ultimate goal is not for us to particularly own it, but for it to be sort of a public commons kind of thing. And I think that is about it. I guess sort of some key learnings from our work in general with the platform here is that, it's pretty involved to make one of these platforms. It's not like it requires some amount of ambitious sort of engineering effort. So there's big benefits to then reusing that work. And it exists. Like we have this thing that can actually do, some form of autonomy evals currently. Yep. Thanks, everyone.